Alrighty. So for my water boiling lab, my procedure, I got a pot. I preheated it on the stove on high heat. By that, I mean I cooked dumplings so I could eat them while I did the lab. Very important. Make sure that you replicate that if you replicate this experiment. Then I made sure that the pot was empty and I put it back on the hot element to make sure that it was kind of preheated. That way I could start with a hot pot every trial. I measured water with a graduated cylinder from my sink. I collected it in a bowl. I had the sink set all the way to the cold side so I could try to control what temperature the water started at, which I measured as 22 degrees Celsius. Then I rapidly poured the water from the bowl into the preheated pot and concurrently, oh gosh, I spelled that wrong, started the timer. Once the water was fully boiling, I stopped the timer, recorded the time, emptied the pot, let the pot preheat for at least 30 seconds before the next trial, and then I did the next trial. So I increased water volume in increments of 100 milliliters, and I took data from 100 to 600 milliliters, and I got two sets of data. So initial temperature 22 degrees, final temperature 100 degrees. These were the volumes that I tried. These were the amounts of seconds that it took to get these volumes to boil in the first trial and then the second trial. So then I wrote some code to get the average of those two times. And then I found the standard error of the mean of the average. So basically you take the um, average, subtract it from the actual time, and then you divide it by the square root of the amount of trials that you took. Um, yeah, so we see that our average times, we had 9.71 seconds for 100 milliliters, 28.5 for 200, 55 for 300, 78 for 400, 92 for 500, and 119 for 600 milliliters. And that was with an error of 1.3 seconds for 100, 1.2 for 200, 2.5 for 3, 1.1 for 4, 2.3 for 5, and 3.9 seconds for 600 milliliters. So that was my error that I had. Um, so here you see a lovely little plot of the data. We've got our amount of time in seconds on the y-axis. We've got our volume in milliliters on the x-axis. Here you can see the average for each trial as these little dots. And then I was also able to find the formula for the line of best fit, which is this orange line here. And so it had a slope of 0.2189. And so the units there would be seconds per milliliter based on our graph. Um, so basically, this seems to be telling us that there are 0.219 seconds for every milliliter of water that you add. You have to add that much more time to get it to boil, is what it seems like my data is saying. So whoa, over here to the argument board. Guiding question. How does the volume affect the rate at which water boils on a stove? My claim is that every additional milliliter of water will add about 0.22 seconds to the total time it takes for a volume of water to heat from 22 degrees Celsius to 100 degrees Celsius. The evidence, after plotting the data, it appears to have a linear relationship. The line of best fit has a slope of 0.2189 seconds per milliliter. So to justify why this proves my claim, when plotting data that has a linear proportionality, the line of best fit illustrates the rate of change between the independent and dependent variables. So 0.2189 seconds per milliliter tells us that according to my data, each additional milliliter of water adds that many seconds to the overall time. And then I kind of got carried away, and this is all really extra, but I'm going to read it anyways, haha. So every trial, I heated a sample of water from 22 to 100 degrees Celsius. So it had a change of 78 degrees Celsius. So we could say that according to my experiment, my stove could heat a milliliter of water by 1 degree Celsius every 0.002806 seconds. And since 1 gram of water is 1 milliliter of water, that conversion is exact because grams and milliliters are based off of each other. We can convert this directly to calories, which is a unit of energy that y'all might be familiar with. Like if you eat food, it has calories or energy. 1 calorie is defined as the energy it takes to increase the temperature of 1,000 grams of water by 1 degree Celsius. And so since we can convert milliliters to grams, we could say that my stove outputs a calorie of heat energy every 2.806 seconds. So we could convert this to joules, which is another form of energy. So every calorie is 4,184 joules. And to go a step further, a watt is a joule per second. So if we take this, we multiply it by 1 calorie, and we divide it by 2.806 seconds, we can see that according to my experiment, my stove seems to use 1,491 watts of power. The hood of my stove says it operates at 220 volts, and that means that there's a huge 6.77 amp current because power equals volts times amps. Um, so I did this divided by that is 6.77. 6.77 amps running through the stove element at this high heat. Um, of course, this is incorrectly assuming that all of the power that the stove is using is converted to heat and that all of the heat goes directly into the water. So the current's probably a little bit higher, probably like 7 to 8 amps. But just to illustrate how high that current is, uh, zero point 0.1 to zero point 0.2 amps across the heart can kill a human. So I thought it was really cool that I could take this information about boiling water and use it to estimate how much current is going around in my little electrical stovetop. Um, yeah, so that's what I did, presented to you in a way. Thank you.